In this presentation, we'll be taking a closer look at how deep learning is helping us create better acoustic detection and classification models for use in passive acoustic monitoring. And we'll also take a look at how deep learning is changing the way that we develop and use these models. Many of you will likely have heard of deep learning, and if you haven't, then likely you'll be familiar with deep learning, or at least it's the technologies that deep learning has made possible in recent years, such as facial recognition algorithms used by apps like Facebook, or object detection algorithms used by software in self-driving cars, or the speak recognition and synthesis algorithms that are used in personal assistant systems such as Amazon's Alexa. Now, in all these cases, these algorithms have been trained on a very large label data set, and that is a big part of the reason why they've become as good as they are. In marine bioacoustics or in underwater acoustics, the label data sets are much smaller typically. But nevertheless, we've seen in the last few years the first successful applications of deep learning to this domain to develop detection classification models. And what we've seen is that the deep learning based detection classification models tend to outperform the more conventional algorithms. And so we're really at a point now where this has been shown to work, and it would be of considerable interest to develop some tools and some software that make these deep learning algorithms accessible to a wider audience of researchers. And this is what we'll talk about today. Now, comparing deep learning to more conventional machine learning, the one sort of big difference is that deep learning aims to be end-to-end. So that is to say, the classification model works directly on the raw original data, whereas in a more conventional machine learning approach, you would have a feature extraction step in which the high-dimensional input data is reduced to just a few, say, a handful of features upon which the classification algorithm acts. And that feature extraction step, importantly, is designed by a human expert, implemented by a human expert, and is often tailored to a very specific data domain. And so instead, in deep learning, this feature extraction step is part of your algorithm, and it's learned from the data. Now, in underwater acoustics, what we often do is not work with the raw data, the waveform itself, but we work with a spectrogram representation of the audio. So we're not fully end-to-end, but it's still a much higher dimensional representation than just a handful of features. Now, with this different approach, this end-to-end approach, this opens up some interesting possibilities. One of them is often referred to as transfer learning. So this is a technique whereby you take a model that has been trained on a rather large label data set to achieve very high performance in terms of classification. And in this case, in the example to the right, you see a model that's been trained to distinguish images of cats and dogs. And then you repurpose this model, so to speak, to perform a slightly different but related task in which it's distinguishing between images of cows and horses. By using this technique of transfer learning, this repurposing of the model can be achieved, can be done with a much smaller labeled data set, because you're reusing the same features. So much of what the neural network, the deep learning model, has learned is reused, and all you're doing, this could be one way of doing it, is to add, say, a layer of neurons at the end of your neural network and just retraining those few neurons to make the final classification. So clearly this opens up some interesting possibilities also in the domain of underwater acoustics, where you could envision repurposing a classification model from one acoustic environment to a slightly different acoustic environment. And this is illustrated by this workflow. So this is kind of what one could envision with a deep learning model, is that you have a pre-trained model that you want to use in a slightly different setting. And so you'll run that model on some data collected in this new acoustic environment. You'll bring in an expert to validate the outputs, the predictions, or the classifications made by the model. And importantly, this expert is not required to modify the model. So the expert is not required to do any math or programming. Just validate the examples. Based on that validation, you build a new training data set, which then is used to retrain this model and adjust or improve its performance. Now, if you would like to develop your own deep learning model, there are several open source software packages out there that will help you do this, one of them being Google's TensorFlow package. But these packages still require a high level of programming efficiency and also a very good understanding of deep learning. And so to make deep learning accessible to a wider range of underwater acoustics researchers, we've developed a high-level interface that we've called Ketos. And this is what I'm going to talk about in the rest of my presentation now. In case you were wondering, the word Ketos comes from ancient Greek, where it means large fish, whale, shark, or sea monster. And of course, Ketos is also the origin of the scientific term for whales, cetaceans. So basically what we've tried to do with Ketos is to provide all the functionalities you would need to develop and train and use a deep learning model for performing detection and classification tasks in underwater acoustics. So Ketos provides functionalities for audio processing, such as computing a spectrogram from a waveform. It provides functionalities for working with annotation tables, functionalities for creating and storing training databases. So this allows you also to work with larger than memory data sets, which is often the case in deep learning. It provides a number of commonly used neural network architectures, such as a few convolutional neural networks. And of course, functionalities for training and repurposing these models and turning them into detector and classifier systems. Ketos is written in Python. It's open source, licensed under the GPL license, which means it's freely available to use and modify. We host it on a GitLab repository, which is an excellent environment for collaborative coding. If you're interested in getting involved with developing Ketos, just reach out. We are very open to bringing more developers on board. And yeah, the code is fully documented with lots of little examples and also more extensive step-by-step tutorials that will help you get started with using the various functionalities of Ketos. And you can get the Ketos software package from the official third-party software repository of Python, the Python package index. Ketos makes use of a number of widely used open source Python packages. For audio data manipulation and processing, we rely primarily on SciPy, NumPy, and Brosa. For data handling and storage, we make use of the HDF5C library and the PyTables interface for this C library. And finally, for the machine learning stuff, we rely primarily on Google's TensorFlow package. As I mentioned, we have extensive documentation of the Ketos package, which you can find at the URL listed here at the top. Of all the things you will find here, again, I would like to draw your attention to the step-by-step tutorials, which provide you a nice entry point to start working with this software package. So I just want to show you one example of where we've used Ketos to develop a acoustic detection system. And so in this particular case, we collaborated with Canadian government researchers from the Department of Fisheries and Oceans on developing a deep learning model for detecting the upcall of the North Atlantic right whale. You see an example of this upcall to the right in the spectrogram. So it's a pretty short duration call of a little over typically a second and a half duration, which spans frequencies from about 100 to 200 hertz, and it's a rather stereotypical call. Our collaborators provided us with several thousand examples of this call, and also several thousand examples of negatives, so noisy clips that did not contain an upcall. And importantly, these upcalls were obtained in different locations with different types of deployment techniques, both surface buoys and bottom moorings. So this ensured that the training set had a high degree of variance, and most importantly, that matched the variance that we expected in the application scenario. We've made this data set available through the Canadian Federated Research Data Repository. You can find it at this DOI. And so if you want to use that for your own model development, you're more than welcome to. In the middle, you see a summary of the performance, the rather satisfactory performance that we achieved in this study, but I won't really go into that anymore. I'll just encourage you, if you're interested, to go to our paper that was published earlier this year in the Journal of Acoustical Society of America. Just as a final thing, I'll just bring to your attention the links at the bottom right. So we did make the code, the full code used in this study available through the Zenodo platform. And you can also, by following the step-by-step tutorials on the Ketos documentation page, you can, these will guide you through the model development and give you a better understanding of how we developed this classifier. So with that, I'm just going to summarize the main points from this presentation. So deep learning is helping us create better detection and classification models for use in passive acoustic monitoring, but it's also changing the way that we develop and use these models. Then the MERIDIAN team has developed a software package called Ketos that we hope will make deep learning accessible to a wider range of researchers in underwater acoustics. Ketos is open source, it's written in Python, and it provides commonly used neural network architectures, functionalities for doing transfer learning, tools for dealing with larger than memory data sets, functionalities for audio processing, saving and sharing of models. So essentially everything you would need to support the full pipeline of developing and using deep learning models. We offer extensive documentation on this package, and then we have step-by-step tutorials, which is a good entry point to start using this package. And I welcome you to check it out at the URL that's provided here at the bottom. And then just as the very final thing, I just like to acknowledge our funders and partners, above all, the Canada Foundation for Innovation, which has funded the MERIDIAN project. And then I'll just leave you with our contact details, and thank you for your attention.